look at capacitors real quick. So all a capacitor is, most of the capacitors are paper type capacitors. So it's a type of material that they use. So this paper here, this type of paper that they use, sometimes it'll be a foil. So it'll be a paper, an insulated paper, and then there's a conductive plate, a foil of some type, and then there's this dielectric material, and then there's a foil on the other side. So we have on the one side, we have the anode conductive plate or foil, and then we have the cathode conductive plate or foil. And the value of the capacitance is finite, meaning that the value of how much capacity this has to store a charge is a function of a couple different things. It's a function of the physical size of these plates. Like the bigger the plate, the greater the capacity I can get of getting more electrons gathered onto that plate. It's also a function of the strength of the dielectric material. So how good is that dielectric material at not allowing current to flow through there? And as well as the distance between these two plates. The greater the distance, the greater the dielectric ability to resist that current flow, the greater the dielectric strength, the greater the capacitance. So what normally will happen is there will be a paper and a foil and a dielectric material and a foil and a paper, and then they roll it up. Think of taking a sheet of paper out of the printer and having a conductive plate on one side with an insulation and a conductive plate on the other side with some insulation, and then just rolling it up. And that's basically, capacitors look like cylinders. If you've ever seen working capacitors, you just very simply look like this. They just look like a cylinder. Just look like a cylinder. And you'll see these on, you'll see these on motors. You'll see these on fan motors. You see them in capacitor banks, and there will be two terminals. There will be a terminal here, and there'll be a terminal here, maybe three terminals. It depends on the type of capacitor. You see them on air conditioning compressors, running caps and starting caps. And when you see one that's bulging, or looks like it's got something coming out of it, it's bulged, it's split, it's got something coming out, that's a dielectric material. So oftentimes when they go bad over years of use, these constant repetitive firing, discharging, and charging cycles, they will sometimes leak. But if a capacitor will always sort of hold a charge, and it's because of this characteristic of the capacitor, where when a capacitor starts to charge, it really starts, and this picture doesn't do it justice, it really charges within its first time constant, or tau, about 63% of its capacity. And effectively by its fifth tau, its fifth time constant, it's effectively charged, but it never really will get to 100% because it's exponential. It'll get to 99.999% or so of its charge, which also means that when it's discharging, which also means that, and if we were to look at this, meter that I've got on the right here, this one here, so I've got an analog meter, and this is how we used to teach this. We don't have access to these analog meters anymore, but I want to show you basically that needle would be, if the capacitor was off or discharged, it would be somewhere around there, okay? Assuming that it's 0.0001% charged. And then as it starts to charge, it gets up to like 63%, and then it slowly gets to its maximum charge, whichever that is at 99.9. Same thing happens when you discharge. It goes to about 63%, and that's just an exponential decay, and then it sort of gets down to somewhere around there. So it is this sort of in terms of electrical, it is a somewhat slow process. But here's what I want you to understand, is that when I apply this power over here, looking down at this little blue circuit, I apply power to this, if I have my power supply, let's say I have this power supply at 7 volts, 7 volts RMS, this capacitor will very, very rapidly charge up to 7 volts RMS. But what is 7 volts RMS to a capacitor? It's really 10 volts peak, isn't it? To a capacitor, because that's what it's seeing. Is it's seeing the total value of charge. Now, an RMS value is just a rooting square plotted across that sine wave. But a voltage peak, hey, that's a lot more. That's 10 volts. So that's why as you add more capacitance, you end up your value of output voltage in these circuits that we're going to be doing is you're going to see them start to increase. Okay, which is kind of cool. This is your full wave bridge rectifier. We're going to come back to this. So we're not going to do anything with this. We're going to come back to this because you're going to be doing half wave bridge rectification. Then we're going to go to full wave bridge rectification with filtering, and we're going to use it for some of our circuits. So this is coming back. We're just not going to do that this week. The interesting thing about capacitors is that, I said when we're trying to understand capacitors that the capacitors, the value of the capacitance is relative to the plate size, the distance between the plates, and the strength of that dielectric material. So let's take a look at how to understand why we have to calculate capacitors in this manner. So let's take a look first, capacitors connected in series over here. Capacitors connected in series. So to calculate capacitance, we're going to use the reciprocal formula. Now you may be saying, hang on a second, in resistors for series circuits, we sum those values of resistance. Well, for capacitors, we do the same thing, but only in parallel. But why do we do the reciprocal of the sum for series connected capacitors and capacitors connected in parallel? Why am I even mentioning this? Just tell me the rule, tell me what I got to do, and I'll do it. No, let's understand why it is the reciprocal in series and why it is the sum in parallel. Well, understanding that the capacitance of a capacitor, its ability to store a charge, is a function of the size of the plate, the distance between the plates, and the strength of the dielectric material. Let's focus on the first thing, the size of the plates. Let's look at the size of this plate here. It's the same as the size of this plate over here, isn't it? But where's the difference? This plate is connected to this plate, and this plate is connected to this plate. Effectively, what we've done is we've tripled our size of that positive potential plate, haven't we? We've tripled its size, so we should get a greater value of capacitance. Remember, series circuits sum to increase the value of resistance. Capacitors in parallel sum to increase the value of capacitance. The total capacitance in a parallel circuit is equal to capacitor 1 plus capacitor 2 plus capacitor 3 because those plates are all effectively tied together, making one big plate, and the same thing for the negative or the cathode side of that cap. Conversely, let's look at capacitors connected in series. They're in if we was to say these were power supplies, and they are similar to a power supply, are they connected series aiding or opposing? Well, they are connected series aiding, okay, positive, negative, but the charge on this one migrates to here. So we never really get a good buildup on the cathode plates. So that's why it's the reciprocal for this one, whereby if I had, say, 10 ohms here, 10 microfarads here, 10 microfarads here, and 10 microfarads here, I would use 10 to the x negative 1 plus 10 to the x negative 1 plus 10 to the x negative 1 equals x negative 1 equals 3.3 microfarad. So the more capacitors I put in parallel, the greater the decrease of the capacitance. Interesting. Okay, so recognize that. A little different, but if you understand that these plates are all connected, increasing the area, thereby increasing the capacitance, that's an easy way to remember it. That's going to allow you to remember it. And why is that important? Because if you remember that, then you remember that it's the sum